Hello friends, this is Professor Ganesh Sattarde from UNTC Department SITRC Nashik. Welcome to the DSA practical video series. Today we are going to see the 8th practical of subject data structure and the algorithm SE NTC 2015 pattern SPPU. The title of the practical is the graph using adjacency matrix with BFS and the DFS traversal. So let's move toward first the theory of this particular practical. Okay, so title is given graph using adjacency matrix with the VFS and the DFS traversal. Aim is write a C program to create the graph using adjacency matrix with BFS and DFS. The objective of this article is to study the graph concept and terminology, graph representation, and the graph traversal. So what is graph? The graph consists of two sets. The first one is a finite set of vertices and the finite possibly empty set of the edges. So there are two types of graph. The first one is a undirected graph and the second one is a directed graph. If in edges, if all the edges are not having the direction, then that type of graph is known as a undirected graph. And if in a graph, if one of the edge is having the if one of the edge or all the edges is having the direction, then it is known as a directed graph. So here some example of the graph is given. Now we will see here how to represent our graph or how to store our graph in a computer. We can store the graph by using the adjacency matrix and by using the linked list. So in our example, we are going to store our graph in terms of the adjacency matrix. So in adjacency matrix, if there is an edge between the Vi and the Vj, then adjacent matrix of I and j is equal to 1. Otherwise, if there is no such edge between the Eg, then the adjacency matrix of I and j equal to 0. So if there is a path available from suppose vertex 1 to vertex 2, then only we are putting 1 there. If there is no such a path is available, then we are putting 0 there. So in this way we are going to store our graph in a computer. So actually there are the two types of graph traversal. The first one is a depth first search traversal and the second one is a breadth first search
It's 11:30.
Traversal. So first we will see the depth first search. In a depth first search, generally the stack data structure is used for traversing. So here let's one example. Here this is one graph is given. It is having the total 6 vertices. Let's start from the A. So if I am starting from the A, so I can move towards E, I can move towards C. So we have to choose one of them. So suppose I am choosing C. So we are going from A to C. Then after that again we have to see the possible path of possible further path from the C. So possible further path is B, F and the D. So we have to choose one of them. So if I am choosing B, then again we have to see the possible path from the B. The possible path from the B is C and the F, but C is already visited, so we are going to the F. So the next path is F. Then again we are now at the F vertex. Now again we have to see the possible vertices or neighbor vertex of the F. The possible neighbor vertices are the B, C, D and the E, out of which the B is visited, C is visited, but D and E is not visited. So we have to choose one of them. Suppose if I am choosing the vertex D. So if I am choosing the vertex D, then I am marking the D as a visited. Then after that again again we are checking the possible neighbor vertex of the D. Now there is no vertex is available which is a neighbor of D which is non-visited. So that's why we will move toward the one step back, that is at the vertex F. Again we are see that if any vertex is remaining which is not visited from F, yeah, there is one vertex remaining, that is E vertex is remaining. So that's why now we are visiting E. Now again the same procedure we will carry it out. Again we are checking that any unvisited vertex is there. No, there is no unvisited vertex from E. So we will move toward the F. Again we will check that any one more unvisited vertex, no. So that's why again we will move to the B. Then again no unvisited vertices, so that's why again we will move to the B. Again no vertices is there which is not visited, so again we will move to the A, and now there is no again vertices are available which is not visited, so that's why we will pop this A. So in this way we are now doing the pushing and popping operation, and using this pushing and operation we will we can search all the graph, and we can visit all the vertices by using this technique. The next one is the BFS, breadth first search. Now in a breadth first search we are using a queue instead of using stack. So how it works, the same example, A, C, D, B, C, F and E, these are the 6 vertices. Suppose I want to start from A, then what the breadth first search is doing, so we have to visit all the neighbor vertices of A. The neighbor vertices of A is C and E. So the your example is your search is A to C and E. So we can go from A to C and then A to E. So A, C, E, these are my visited vertices. Then after that, now we are DQ'd A because all the vertices of A is visited. So now next one is C. So we have to DQ C, but before DQ C, we have to check that we have to visit all the unvisited neighbor vertices of the C. So unvisited neighbor vertices is B, F and D. So that's why we are visiting that. So the then first we are visiting B, then D and the F. Then we are again move toward the B. So no remaining vertices are available here, also no remaining vertices. D is also not having the remaining unvisited vertices. E is also not having remaining vertices. That's why the traversal is A, C, E, then B, D and F. So this is my BFS traversal. So we can achieve this, we can visit all the vertices by using a BFS traversal, and remember that BFS traversal uses the Q data structure. So let's move toward the theory practical part of this particular practical. So clear. So my program is, first I am divided this practical into two parts. First one is DFS traversal, second one is BFS traversal. So nano experiment 8A.c. Now first one is derive traversal using a DFS algorithm. Next one is hash include stdio, then define max is 10. That is my now DFS traversal requires the stack, so that's why I am using here the max size of this stack as a 10. Then I'm using the preprocessor directive true and false as a 1 and 0. Then one function I'm declaring DFS, which is responsible for visiting all the nodes or traversing. The next one is here one adjacency matrix is given. Generally the adjacency matrix is used for showing your graph. The next one is visited array. So if one of the node is visited, then we are making the 1 in this visited array. If it is not visited, then we are making 0 in that visited array. Then n, here one variable is there. Now next one is enter the number of vertices that is stored in the n. Read the adjacency matrix. Generally adjacency matrix is nothing but the 2 by 2 your n by n matrix. So n by n, for n getting the n by n, I am using the for outer for loop and inner for loop, and in that between the scanf percentage the address of adjacency of I and j. Next one is initialize all the visited to 0, so that's why visited of I is equal to 0, all the visited of I is equal to 0. Then DFS of 0, so starting vertex I am taking as a 0, so that's why I am passing its argument as a 0. So I am calling the DFS function. Here the DFS function is called. Then here I am declaring a stack. The top variable I am declaring. I am initializing top is equal to -1, top plus, and one first vertex I am inserting, that is V. So first vertex is 0, so your first entry in your visited is 0. Next one is the while top is greater than or equal to 0, then x is equal to top of 0. First we have to remove the top of the stack, then top minus, then after that we have to check that visited of x, that is equal to false. If it is equal to false, then we have to make it as a true. If it is already true, then we have to check for the next vertices. So if it is false, then we are making it as a true. Then next one is for I is equal to n, I greater than or equal to I minus. So it means that for every vertices of that particular vertex, neighbor vertices of that particular vertex, we are checking that it is visited, any unvisited nodes or unvisited vertices are available or not. So if adjacency of x of I equal to 1, that is if it is neighbor, and visited of I equal to false, so it is non-visited. If both conditions are true, then only your element is pushed into the stack. So similarly, the same process is repeated until your stack becomes empty, and your DFS traversal is over, and it is printed. Your DFS traversal is printed. Then next one is printf, that is I am printing the new line and return 0. So let's first check this program. Control X Y. Now there is one example, BFS traversal. Okay, look at this example carefully. Now here one graph is given. Graph is having 1 2 3 4 5 6 7 8 vertices. Here using the graph I have constructed one adjacency matrix. So you can see here there is no path from 0 to 0, so that's why 0 to 0 is 0. Now suppose there is path is available from 0 to 1, so that's why I am making from 0 there is a path is available to 1, so I am making it as a 1. Now from 0 there is no path available from 0 to 2, so that's why from 0 to 2 I am making it as a 0. Similarly, the remaining vertices and the edges are marked here. 1 represent it is a neighbor vertex, and the 0 represent it is a non-neighbor vertex. We have to check it is a solution by it is solved by using manual. So we have to check whether it is giving the same, your program is giving the same output or not. So first we have to compile it. So for compilation, GCC -O, then EXPT8, then EXPT8A.C. Okay, compile successfully, then /EXPT8. Number of vertices, how many vertices are there? 8 vertices. Okay, now first we have to enter the adjacency matrix. So 0 1 0 1, then 0, then 1, then 0, and then 1 2 3. Okay, the next one is 1 0 1 0 1 0 1 and 1 0 1 and 0. You have to enter this adjacency matrix very carefully. Next one is 0 1 0 1 1 0 1 and 0, then 1 0 1 0 0 1 0 and 1, then fourth 0 1 1 0 0 0 1 and 0, then 5 1 0 0 1 0 0 0 and 1, last one is 1. The next one is 0 1 1 0 1 0 0 0, then 1 0 0 1 0 1 0 and 0. Okay, so let's check. Okay, so here the output is given as 0 1 2 3 5 7 4 and 6. You can check here the DFS traversal. 0 1 2 3 5 7 4 6. Yeah, 0 1 2 3 5 7 4 6. So in this way we will get the output. So this is all about the your DFS traversal. So next move toward the BFS traversal. So for BFS traversal I am opening the 8B. Similarly here in the last example for DFS traversal we have used the which data structure? Stack data structure. But for BFS data structure, BFS traversal, we are using the queue data structure. Similarly the main program is very same, only one difference, instead of DFS we are using BFS. Now next move toward the BFS. Similarly, the front here the queue is initialized, then visited of v is equal to true, that is first node I am visited, then rear plus plus front plus plus, then I am first DQ. Yeah, then after that while front is greater than or equal to rear, so it is an empty condition, so v is equal to q of front and front plus plus. Now again same thing, we have to check whether your vertex is adjacent and here it is a non visited node, non visited vertex. So that's why we are checking here the condition adjacency of v of I equal to 1 and visited of I equal to false. Then if it is false and it is this is equal to 1, then printf I, that is your it is printed, and then visited of I equal to true and real plus plus and q of re, that is it is inserted into the queue, and it is repeated until your queue becomes empty. So we are checking here I am making one printf statement. So slash n at bfs traversal is slash n. So control x y compilation for compilation 8b dot c dot slash expt 8 that is whatever you are giving your binary name. Okay, number of vertices. So we are taking the different graph for BFS. This the graph is given. Okay, how many vertices? 1 2 3 4 5 6 7 7 vertices are there. Adjacency matrix is 0 1 1 0 0 0 1, then 1 0 1 0 0 1 and 0, then 1 1 0 1 1 1 1, then 0 0 1 0 1 0 1, then 0 0 1 1 0 1 and 0, then 0 1 1 0 1 0 0, then 1 0 1 1 0 0 0. Okay, and the BFS traversal is 1 2 6 5 3 4. Okay, so here and here the same answer we will get 0 1 2 3 0 1 2 6 5 3 4, and here we are getting the same answer. So in this way we have to check whether you have to construct your own graph, and you have to check whether you are getting the same output that you have calculated manually. Okay, thank you very much.